So when we're talking about telescopes, then we need to talk about the tools that you're using in astronomy. And that's what a telescope is. But modern telescopes, you don't normally just look through the eyepiece. Amateur telescopes, yeah, you look through the eyepiece. But for professionals, you no longer just look through the eyepiece. You're using instruments attached to the telescope. Spectrometers, for example, that measure the spectrum of something, photometers that measure the brightness, cameras that record an image objectively, not just what you think you see, but record what's really there. The advantage of a camera is that it also allows you to do time exposure pictures. The longer the camera is looking at something, then the dimmer it sees, up to a point. So what we're going to talk about next are the instruments you actually attach to telescopes. One of the first ones being obviously the camera. And in the old days, cameras used chemicals, that when the light hits the chemical, it caused a chemical reaction, and then you developed it and you had a picture. Okay, so that evolved from originally just pieces of glass that had the chemicals smeared on them, glass plates that were the first instruments, the first things that you used, later to film technology. But an interesting thing happened over at Texas Instruments in Dallas. There was an engineer that was looking at some other sort of things, and he was looking at the possibility of using a semiconductor and using the photoelectric effect. When light hits the semiconductor, it knocked electrons loose, but the semiconductor didn't allow the electrons to run anywhere, so they just accumulated where the light was hitting. And then later you could adjust the voltage to move those electrons off and read how many were located where in which pixel of the CCD, or of the semiconductor. They call it a charge coupled device. He originally was going to use this as a type of optical storage instead of magnetic storage, but colleagues of his realized that you could actually take this CCD and replace film with a CCD, and the light would hit it. So what we got here is some examples here. We've got a CCD right here off to the left, and these three pictures. This picture right here was taken with film. This was a CCD. Now, because it's a computer that's reading off the CCD, then that means it's a digital thing. And one of the things they'd started doing was digitizing the film pictures and then letting the computer process them and get extra information. Well, this is already digital, so that means you can process it and get the information much more readily. And so the image on the right was taken with a CCD. It takes less time to get a time exposure picture. It's more sensitive, and because it's already digital, you can do all the other processing. For example, you record exactly how much charge is in which spot that relates to how bright it is, and that way you can do photometry with the CCD. Not just make a pretty picture, but you can make measurements with it. And so that's the kind of the idea. Originally, astronomical CCDs were fairly large instruments on the back end of the telescope. You had to cool them to very low temperatures, so there's no electronic noise. The electronic noise would basically just put extra dots into the image, and of course the extra dots would be just mistaken for stars. And so you had to cool them. Modern CCDs are getting more and more sensitive to the point that you don't need to have the external cooling. In fact, the CCD technology has evolved so that every digital camera now is a CCD. That's where they come from. And so they are very sensitive, very, very well developed technology, and you can now take an SLR camera and just attach it to the back of a telescope, or there's even now ways of taking your phone and use the camera on the phone to the back end of an amateur telescope to get images. Now, those kind of CCDs don't carry as much information in them necessarily as the more professional grade ones, so you can't do quite as much science, but you can definitely get really good, pretty pictures. So the CCD has displaced film as the medium of choice for astronomers. The other issue we've talked about is that these large telescopes, gravity, and even temperature can change the shape of the mirror. It goes out of focus, so to fix that, what you typically would do is adjust the mirror. So this is active optics. So an example of active optics is already the Keck telescope or the Hubble telescope or any of these other segmented mirrors. You point the telescope into the upper atmosphere, you fluoresce a piece of the upper atmosphere, the mesosphere, with a laser, and you image on it, and then you adjust the shape of the mirror to make sure that all the light is focusing properly. Using active optics, you can build vastly larger telescopes. That's the dome of the Hubble telescope, and then there's the laser right there, the laser tower. It's black on the back side of it facing the instrument so that when you're looking off in that general direction, you don't have an object in the way reflecting light. Now, the other sort of technology that we have here is what we call adaptive optics. And the other problem that you have with looking through the Earth's atmosphere is that the atmosphere itself distorts what you're looking at. And so as the atmosphere is distorting an image, you get this shimmering sort of effect, twinkling of the stars, different parts of a planet being in focus or out of focus as the light is shining through different parts of the atmosphere, with a big mirror even, as I said, the bigger the mirror, the sharper the view up to a point. Once you get to a certain point, just little micro convections in the atmosphere blur things. So once you get a mirror that's more than about 12 to 14 inches in diameter, then you quit gaining a whole lot by making the mirror bigger. You can see dimmer things, but you don't see it really much sharper. And so an idea they came up with is to have the light hit a variable mirror, reflects off the variable mirror, hits what we call a beam splitter. So half the light goes on as focused to a CCD, half the light is bouncing off to a detector that detects these tiny little variations here. The detector is connected to computers that then controls this first mirror, and it moves a little bit, so the surface moves to put everything back into a coherence. And so what you end up with is a clearer view, as if the atmosphere weren't there. Now, it's not perfect. You throw away half of the light right here, so you can't see something quite as dim. And it only works so well, but it does work better than nothing. And so this is a fantastic tool. Here's an example right here, the planet Neptune without the adaptive optics. One of the best pictures from Earth. You turn on the adaptive optics, same telescope and same camera, and you can see cloud bands and structures and a big storm on the planet Neptune. Likewise, if you look into the center of the galaxy, without adaptive optics, all the light of the stars blurs together here, and you just get a smear. With adaptive optics, then you get the individual stars. And so that allows us to see a lot more detail than we would otherwise have been able to see. And so adaptive optics, active optics, CCDs, these have really taken over and changed a lot of things. That's not the whole story. Okay, it's not just pictures. We have photometers that you can use to measure the brightness of something, and this is actually almost exactly the kind of photometer that I used in graduate school to measure brightnesses of variable stars, and so it measures to very high precision the magnitudes. The other thing is you can use a spectrograph. Take the light and then split the light into all the different colors of the spectrum. Well, with that, you can see the spectral lines, the individual spectral lines that make up the light. Okay, and so that way you can find the chemical composition of something. Remember, we talked in the chapter and all the stuff there about light. we talked about the things where you can do things with the light and measure the spectral lines that tell you the chemical composition, how shifted the spectral lines are, can tell you the Doppler shift, the radial velocity. The other thing you can do with the spectral lines is that they can tell you the size of the star. I mean, all these different things you can learn with the spectral lines. And so they turn out to be very, very important. And so spectrometers, astronomical spectrometers, are a major instrument. And so it's one of the very first things you do when you make a discovery is you take a spectrum of it. And so with that, that's our discussion of the instruments that you put into the telescope. And so that's a major step right there.